Welcome everybody, that's a new tutorial on truss analysis, but this time we're going to use the method of sections. So my first question is, why use the method of sections in the first place? We know from from your statics or structure analysis class that the two major methods that usually we use in analyzing trusses are the method of joints and method of sections. The method of joints is most effective when the forces in all the members of a truss are to be determined. But if the force you are interested in few members of these of the entire truss, let's say the truss has 10 members, and you are all interested in checking or knowing the magnitude and the type of the force in a certain member or a group of members, let's say 3-4 of them, your best bet is to use the method of sections because it's more efficient. Basically how it works. Without going into so much details, the basic idea is you cut the truss into two parts through the members that you are interested in finding their forces. And remember, the entire structure is in equilibrium, right? So the summation of bending moments created by the interior forces exposed, the interior forces I'm talking about here, and we will see this in more detail later. The interior forces of the members that you exposed by cutting the truss, they create moments. The summation of these moments about any joint of the truss should be equal to 0. So let's take a look here. We have this truss. Imagine if you want to find the forces in all of the members. Okay, method of joints again. But what if I told you I'm only interested in the forces in members LK, CK, and member CD? You can see there is a cut line through these members. So I'm gonna cut through the members I just mentioned, and I'm gonna expose the forces inside them. We can see that in LK you either look at the right segment of the truss or the left. So if we look at the left, we have a force LK and we assume it's in tension, and we have a force CK and we assume again it's in tension, and force CD, and we always assume it's in tension just to keep our sign convention consistent. But I'm going to teach you today how to cut the truss. I'm going to tell you the trick behind cutting a truss, or how can you use the what are the basic rules in cutting these members. Okay, the guidelines I'm going to talk about. Okay, first, obvious, cut the members that you are interested in. Remember, your first step, go through the members you are interested in. Okay, obviously it's an obvious thing to do because you want to expose the interior forces inside these members so you can calculate them. Then cut the truss completely into two parts. Don't go through the truss without cutting it from top to bottom or side to side. Don't cut it part way, just go through the entire, then stop. Cut a maximum of 3 members. Remember, if you cut, you need to cut up to 3 members, okay? If you cut 2 members or fewer than 3 members, it's okay. But once you expose more forces, the problem is you may have some difficulties applying the equations or following the method I'm gonna show you. Okay, we're gonna go over them again. So first, cut the member that you are interested in. Cut the truss completely into 2 parts. Cut a maximum of 3 members. So let's take a look. This is the same truss we saw a minute ago. Let's try to apply the 3 rules. Did we cut the members we are interested in? Yes, we did. We cut through the member LK, CK, and CD. Did we cut the truss completely into 2 parts? Obviously, you can see in the figure. Yes, we did. We have a left side and a right side of the truss. Did we cut a maximum of 3 members? Yes, we did. We cut only 3 members. This is the left part of the truss showing the exposed forces. Choose one part to work with. Okay, let's jump into an example. This is a very simple and quick example to do, just to show you the method. So for the truss shown in the figure, determine the forces in members BC, HC, and HG. Here's the solution. First of all, you need to draw the free body diagram. In other words, you need to find the reactions at A and E, which are AY and EY. Now, these reactions are easy to compute just by inspection. The reaction AY and EY are easy to find since the truss has a symmetrical loading about joint G. What I'm trying to tell you that if you cut through member CG, you're gonna find a mirror that joint H, for example, is carrying 30 kilonewtons and joint F on the other side carrying 30 kilonewtons, and in the middle there is one load which is 60. So you can think of the 30 kilonewtons on the left is carried by A, the support A, and the 30 kilonewtons on the right is carried by support E. And the 60 kilonewton is divided equally between supports A and E, so you end up having AY equals EY equals 60 kilonewtons. Now let's slice the truss. Remember, we need to find the forces in BC, HC, and HG. So we slice through the desired members. This is the figure. So what kind of forces are we exposing here? First one is BC, and again we assume it's in tension. Second one is HC, we assume it's in tension again. And the third one is HG, and again it's assumed a tension force. And we will assume, as I just said, that the members are the forces in the members are pointing outwards, so the forces are initially assumed to be in tension. Okay, let's say we went through the analysis and we came up with numbers. What if my number, the magnitude of the force BC, was a negative? That means my assumption was wrong. I mean, the direction of the force was wrong, or the type of the force was wrong, since I assumed everything to be in tension. And let's say I got a negative value for BC. That means BC should be in compression. Since this segment of the truss is in equilibrium, the three equation of equilibrium applies. The summation of the forces in the x direction is 0, summation of the forces in the y direction is 0, and the summation of the moments about a point in this piece of the structure is 0. So we can use these equations, but we will use the moment equation, which is much faster for most of the cases, much faster in finding the unknowns. Yet you have to be smart to pick the joint you are summing the moments about. So what is this deal with the moment equation? Basically, the moment equation, you're gonna use it to sum the unknown forces about a point. Let's say you picked point A, for example, or joint A. So you're gonna sum the forces that you see in this piece of the structure about point A. Now, how many unknown forces do I have, and where are they? I have 3 unknown forces. So the trick here is to find a point that, if I take the summation of the moments about, 2 of the unknown forces will cancel. That means I will end up having only 1 unknown force in one equation, so it's solvable. This is the trick. Since we have 3 unknown forces to solve for, it will be smart to choose a joint for moment summation in such a way that the line of action of all other unknown forces passes through that joint. This way we end up with 1 unknown force in the moment equation, and we can solve for that unknown force. Let's see it in action. First, the force BC. So how many points, or how many points I can solve, or I can do the summation of moments about? I can do the summation of moments about point B, about point H, and about point A. Let's examine them. If I take, remember, I'm solving for BC. So if I take the summation of the moments about point B, obviously my unknown BC, the line of action of force BC, will pass through B. That's not good. Actually, if I take the summation about B, I can get the values for HG or HC. Okay, what are the other candidates? Point A. If I take the summation about point A, okay, BC doesn't pass through A, perfect, so I can solve for BC. But let's double check. What about the other forces? The unknown forces, I mean. HC, it doesn't pass through A. HG, it does. So A, well, something about A will cancel HG, but I still have two unknowns, BC and HC. So I'm left with only one choice, which is H, but let's examine H. If I take the summation of the moments about H, BC doesn't pass through H, that's good, so my unknown is solvable. And the beauty about point H, that both of the unknown forces, HC and HG, their line of actions, both of them pass through H. And one more thing, the 30 kilonewton passes through, so that's a perfect point to choose. If we take the summation of the moments of the forces about joint H, the line of action of forces HC and HG will pass through the joint and will not be included in the moment equation. So this is my summation of the moments about H, and I will assume the counterclockwise direction to be the positive. Okay, so what do we have? We have BC times 4, and it should have a negative sign since the direction of the rotation is clockwise, which is opposing what I'm assuming to be positive, which is the counterclockwise. Then the 30 kilonewtons will not play into the equation. Hg passes through H, so it doesn't play into the equation. Hc, same thing. So I'm left with the 60 kilonewton, the reaction at A. So I'll do 60 times 5, and it's rotating clockwise, so it should have a negative sign. And if I solve for BC, I will end up having negative 75 kilonewton. And since I assumed everything to be positive if in tension, and now, or let me say it the other way, if I assumed everything to be in tension if positive, now I have a negative value, so it should be in compression. Second force, Hg. Okay, so what kind of point I want to choose for Hg? I want a point that will eliminate BC and HC. One might argue, but you just found BC. What if it was wrong? I mean, we all make mistakes, right? So let's try, think of member HG as your first member to find the force in. So what kind of a joint would you have that will have both forces BC and HC pass through? They both go toward joint C. So following the same logic, we will take the summation of moments about a point where two forces pass through. That will be joint C, and summation of the forces about C. Okay, 60 times 10, and it's clockwise, so it's negative, plus 30 times 5, which is counterclockwise, so that's why it's positive. Then Hg times 4, and it's counterclockwise, so it's a positive. Now if I solve for Hg, I will find it to be 112.5 kilonewtons, and since it's positive, it will be in tension. Now we have 2 out of 3, one more to go. The force Hc. One might say, okay, HC, I can rotate it about B, I can rotate it about A, but there is a simpler trick to this. Look at the other two forces, BC and HG. Do you know the values for those? Yes, now you do. So why don't you use the other equilibrium equations? What about summation of the forces in the X and summation of the forces in the Y? Unfortunately for the inclined members, it's kind of difficult to go ahead and find the force in these members directly without having help from the other two forces that you found earlier. So we're gonna assume that BC and HG are correct, and we're gonna use the other one of the or both of the other equilibrium equations, which are the summation of the forces in the X and the summation of the forces in the Y direction. We need to sum the moments about a point in the section shown, but this time we have all the other internal forces known to us from previous steps. Okay, it's easier to resolve force HC into its components. HC will have two components, one in the X direction and one in the Y direction. Then we can use summation of the forces in the X or summation of the forces in the Y to solve for the unknown value of the force HC. Okay, this triangle shows the members HC, HG, and CG. We have HG to be 5 meters, the length of HG. The length of CG is 4 meters, and we need to find the length of the member HC. How can we find this? Okay, Pythagorean, square root, sum of the squares. I will have L to be the square root of 41. Now, if I have a force that is along HC, its X component will be the 5 over L, or in other words 5 over 41 times the magnitude of the force along edge C, and the vertical component will be 4 divided by L, or in other words 4 divided by the square root of 41 multiplied by the magnitude of the force along HC. So how does it look like? The X component, as we can see here, it's HC multiplied by 5 over the square root of 41. So HC is the magnitude, or the magnitude you are looking for, multiplied by 5 over 41. And remember, the easiest way to remember this, you take the whatever length on the x-axis divided by the length L and multiplied by the magnitude of the force. So we do the same trick for the Y direction. We take the Y length, which is the vertical length, which is 4, and divide it by L, which is the square root of 41, and multiply it by HC. Now take a look at this figure. Now we don't have an inclined member or an inclined force. All we can do now is just either use the summation of the forces in the X direction or summation of the forces in the Y direction, but we're going to use both just to double check. So summation of the forces. Let us do the summation in the Y direction first. Summation of the force in the Y, I will have HC multiplied by 4 over 41, the square root of 41, minus 30 plus 60, that should equal to 0, and if I solve for HC, I will have a positive 48 kilonewtons. That means it's in tension. I'm done. But let's double check on our number. Let's do the summation of the forces in the X direction. Summation of the forces in the X direction should equal to 0. It's HC multiplied by 5 over the square root of 41 plus minus 75, which is the value of the force BC, plus 112.5 or 112.5 kilonewtons is the force HG, that will equal to 0. And if I solve for HC, trust me, it's going to be 48 kilonewtons and it's in tension. Am I done? One more step. Summarize all your answers in a table. This way it's easier for whoever's checking your work or checking your answers if it's your professor. We can summarize it into this table. Member BC has a magnitude of 75 and it's a compression or compressing force. HG has a magnitude of 112.5 and it's a tension force, and the force HC, or the force in member HC, it's 48 and it's in tension. So that's it for today, and I hope I clarified this topic for you, and hopefully we're going to work on other problems later on. Thank you.